This is Algebra 1, Term 3, Lesson 6. Today we're looking at geometric sequences. We'll begin in our slides with some basic patterns and a would you rather task, followed by Mathagon, a quick lesson on the differences between arithmetic and geometric sequences, and then Desmos Classroom. So let's start with the slides. This first number pattern is a basic review. Hopefully they remember what an arithmetic sequence looks like and they can create an equation for this one. If anybody's still struggling, this would be a good time to reinforce and help them figure out what they need to know. The next pattern is just something different. Our goal is to kind of get them to step outside that arithmetic sequence bubble and see if they can come up with some other ideas about what's happening with this pattern. I wouldn't say anything. I would just have them maybe list out maybe the numbers and how they think they're growing. So this is just an exploration at this point. And then we've got lots of patterns here. So you can go across or down, but there's different levels of this one, so they can look at each one and try to make sense of it. I'll list out the sequences they can pick out, so maybe the top row, the middle row, the bottom row, the first column, the second column, third column, and so forth. So just have them list out the numbers, talk about how they're changing. Again, we're just trying to kind of get them thinking about patterns that are not linear. So once they've done these three, this is basically a warm-up. They're going to jump right into the would you rather task. So I've given you very little here. I basically tell them in their show notes that the teacher will show you a video. So let me take you to the site and then we can talk about what it is this task will entail. Now you have lots of opportunities here. You can do much more than what I am suggesting. So if you'd like to do all of these tasks, this is the main task. Would you like $1 million or would you like a penny the first day and then double it? You may notice these are Canadian pennies because this guy's in Canada. So you might want to point that out. But even in Canada, a penny's still not much money. So here's task 1. Here they're saying $10 or a penny a day. So this one's a linear function. Then they do another one. Task 2, $10 or 1 penny on day 2, 2 on day 2, 4 on day 3, and etc. And then the main event is $1 million, or you get a penny and double it each day. So this is the one. The main event is the only one I thought you would do. What I discovered is my students had already done this task in 8th grade, so it kind of spoiled the surprise, and it didn't turn out to be as nearly as much fun as I had hoped. So that may happen with your kids too. I don't know how your curriculum before your Algebra 1 class is, but if you have exponential functions, exponential growth, or these types of patterns or sequences, this may be review. So the time that you spend on this lesson will largely depend on your students' background here. I'm not asking them to write equations at this point. They can basically create number lists of numbers. They could create tables. But I do tell them in their notes, tables, graphs, equations, or like tables or graphs or equations, whatever you need to show me, however you want to show me this data, go ahead and do that here, and then they will make their final decision. So the first slide is your just knee-jerk reaction before you do any calculating. Which one would you pick? And then the next slide will be, okay, now that you've crunched the numbers, you've looked at the data closely, now what? So here is a team currently working on this task on the boards, and they immediately, I'd say most of the teams chose to list these out in tables. So you can see that here. So I'm not expecting them to come up with equations, but I did put that down here in their notes, make a table, graph, or equation. So whatever they need to do to figure out what's happening and then which option makes the most sense now. So this will lead nicely into the next task, which is Mathagon. Now when they get into Mathagon, they have already done the introduction, and so the next thing in here is the arithmetic and geometric sequences. So what they will do is they will read these questions or read this information and put answers here. They do have the option of kind of bypassing. Right up here it says reveal all steps. I don't really talk about that because I don't really want them to bypass it. I want them to work it out. But until you do this answer, they will not be able to go forward unless they do either reveal all steps or skip to the next step. So I'm sure some kids will do it. This one is telling you it's 76 years. So if they couldn't figure this answer out, it'll be here, and then they're going to add 76 to each one of these. This is an arithmetic sequence. So as they go through, they're going to play this little bouncy ball thing, which is kind of cool. And as you can see now, they're looking at different types of patterns. So notice you're multiplying. You're getting 80% of the previous height each time. And so they're filling most of these out. You only have to fill in 2. Now this guy sometimes gives you hints or cheers you on if you're doing it correctly. But just have them go through this task and then do their definitions. Some of this they will know because they've done arithmetic sequences and they've done geometric sequences. So the definitions are both here. And then they have some number patterns. So some of these are going to be arithmetic and some are geometric. If they, what's cool about these is they don't just ask you for whether it's arithmetic or geometric. They're also asking for the common ratio, which is R, or they're asking for the common difference, which is D. So they're practicing some pretty important skill besides just determining, but besides just classifying. And then they graph both. What's cool here is they're telling you change these. So you may want to tell the kids, go ahead and change these. And let's start with a negative. What's that going to do? Go back to the negatives here. What does that do to this graph? And if they go to a negative here, what does that do? Which I think this is extremely cool. So have them play with this and make sense of it. The time you spend in here, I mean, they can work on this completely independently. You could put it up in front of the class and ask questions. However you want to do it. I usually have them work through it independently, and then at the end I go show something like this and talk about it and ask them a few guiding questions to make sure. And then you just keep going. So I'm not going to do them all for you, but this is a fantastic resource. It's basically a free online textbook with interactive features. So I like to sometimes, especially when I'm introducing new vocabulary, use this. It's a real great way and an interactive way for the kids to work with these concepts. So once you're done with Mathagon, we're going to move on now to the Desmos activity. Alright, so this is Intro to Geometric Sequences. So we're really focusing in on this particular type of sequence. So they're going to begin with these sequences, and they're to basically try to see what's the same, what's different about these sequences. So they may notice things like, well, some of these numbers are really big. Some of these numbers are small. One of these has a decimal in it. That would make it different. So they may look at some surface level things like that, but we want them to eventually get to what's happening. How is it going from one number in the sequence to the next? And how is that same for every sequence? What's the same? And how are they different? Like the ellipsis at the end, this little dot, 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 and then this one doesn't have that. So what's going on there? So you can have quite a bit of conversation here. We are going to circle back to this slide or this screen at the end of the lesson. So, you know, I guess depending on how much you want to talk about it now, you could talk about it then. But you definitely want to get them to look kind of at the details here and talk about it. The next one, they're going to basically talk about a piece of paper. I would actually give them a piece of paper. I mean, I did that when I taught this. Gave them a piece of paper. I had them cut it in half. Now, a typical piece of paper is 8.5 by 11. So these are not exactly the same numbers of a typical piece of notebook paper, copy paper. But that's okay. We'll just pretend it's 8 by 10. What would happen if you cut it in half and you stack it on top of each other, cut it in half? So you could maybe do a couple just to give them the idea, or even tear it in half. You're going to have a mess, though, if you have them tearing it, just to let you know. But I have them record that information in the table. These are self-checking I don't think it tells them, but it tells you in the dashboard. So you could put your dashboard up and anonymize the dashboard so they don't know who's who, but they could see if they got everything right. This one, they're going to actually see the graph. So what this does is it actually graphs the data from the prior screen on this graph. And I'm asking them to tell me the common ratio and tell me why this graph is a discrete graph. So we're going back and pulling in counting versus measuring for discrete graphs. And then this common ratio, again, where do you see it in the graph? This is your areas this time. Where do you see that in the graph? I do have teacher notes and sample responses on most of these, so be sure to check those before you begin the lesson. To see what it is you're trying to get the kids to notice, and use your questioning to guide them to see it. I mean, that's our goal. Here we have a generalized pattern. The number of cuts is 0, 1, 2, 3, 4, 5. That's important to note that these are not the term numbers. So when they're writing this equation P of n, it is not based on the term number. It's based on the cuts. I have a pretty extensive notes down here in the teacher moves about this. So be sure to read these before you get in here, because this is a common mistake. I would say it's one of the toughest things about exponential functions versus geometric sequences. We start at 1 in sequences. We don't start at 0. We start at 0. Or we could start before that with some exponentials, but we never start at 1. I mean, rarely start at 1. So that's what makes them different. So this, again, 0 is your x, your output is 80. Follow this pattern. What would be an expression to represent the nth cut? Now, when you're doing these, you may want to pause or to pace your class so they're not jumping ahead to get these expressions, because these expressions kind of give things away in the previous slides. So here I'm saying the same exact thing, but let's add in the term number. So if we wrote a different equation this time and did not use the cuts 0, 1, 2, 3, but the term number 1, 2, 3, 4, how would that change your equation? And of course, we're getting into a transformation. You're basically moving the graph right one space to make it fit. And so that's a good point, good time to bring that back, that concept back here. I do have notes about that as well. Now this is just practice. They're continuing these geometric sequence patterns in this table. I did give them the graphing calculator. They can pull that over to the side. The common ratio, I do also use the term multiplier and growth factor. So those are the 3 terms we see. We also have a decay factor, which we'll talk about in a future lesson, but all of these words might be used when you're having a conversation about this task and some of these others. All right, now on this one, they're given term 1, so now we're using the term number. So just like before, when we started at 0, that's actually a lot easier if we could start with a 0, but we start at 1. So think about how that impacts the equation. They need to create a graph for this, so it's important that it's discrete. So if you're seeing kids connecting the dots, you might want to come over and talk to them. So show me that number in your table. Then they're going to choose one of the sequences that was back on screen 1. So this is where you want to make sure everything's open, because they got to go all the way back to screen 1. Pick a sequence, and then they're going to write an equation for that sequence and give the domain for that chosen sequence. Please note, some of those sequences are finite and some are infinite. And I do have some notes here on this screen for you to talk about finite and infinite. So be sure that you address that, because there is a difference in the domains for those types of sequences. And then finally, they're going to create their own. So they'll create a geometric sequence. So at this point, they should know they need to multiply by a number. What is the domain of your sequence? Write an equation and graph it. Now, this graph is kind of limited. So if they just really don't want to limit it to this screen, they have the option of uploading a picture of a graph. So they could make a graph and put it in that way and leave this blank. if they want to. They would type a sequence of numbers, so list out the numbers where it says sequence, domain of their sequence, and then an equation for their sequence. This particular screen would make an excellent artifact in their portfolio. So this concludes our geometric sequences lesson. Next, we're going to work on exponential functions. And of course, geometric sequences is just one type of exponential function. Y'all have a great day.